Good morning, Professor. Myself, Komal Gangavarapu. Today, I'm presenting my project on optimizing file system on heterogeneous memory by integrating DRAM cache with virtual memory management. And this is a third part of the project. I've already submitted the first two parts of the project. And coming to the introduction, okay, the main focus of for the talk, which is optimizing file system on heterogeneous memory architectures, is introduced on the slide. It starts off by outlining the newest advancements in precision memory, called particular attention to 3DX point, CXL based SSDs. These technology, which often non-volatile memory with the possibility of high speed data access and retention even when power is lost, constitute a significant advancement in memory storage. The outline notation of the heterogeneous memory, encompassing both non-volatile precision memory, which usually called short form PM, and the volatile DRAM. When non-volatile PM precision memory maintains data without power, it typically has a lower or slower access speed than the DRAM. Volatile DRAM is renowned for high speed, but it loses data when power is off. While having two forms of memory in one system opens up possibility of optimization. It also introduces complexity in memory management and data access patterns. Yeah, that's it. Heterogeneous memory are volatile DRAM and non-volatile precision memories. Coming to the next slide. Okay, file system categories. This slide categorized for the two primary approaches to leveraging the heterogeneous memory in the file system. Designs using DRAM as a cache for precision memory and employing direct access to bypass DRAM and direct access the precision memory. The first approach, a DRAM cache, utilizes DRAM as a caching layer for the precision memory. In this setup, frequently accessed data is stored in the DRAM cache, leveraging its high access speed capabilities to accelerate overall performance. This method aims to combine the speed of the DRAM with non-volatile nature of the precision memory, allowing for the faster read and write operations while ensuring data precisions. The second approach, the direct access or bypass the DRAM cache and direct access precision memory directly. This method eliminates the latency introduced by the intermediate cache layer, providing more straightforward path to the precision memory. Direct access is designed to reduce overhead and latency by direct interacting with the precision memory, thereby speeding up data access and modifications. However, the both approaches face significant issues that lead to suboptimal performance. The slide highlights the excessive data movement is a common challenge in these systems. In the DRAM cache approach, data must be transferred between application buffer and the DRAM cache, incurring performance penalty. The similarity direct access must handle direct interaction with the precision memory, which can result in inefficient data management and increased latency under the certain conditions. And that's all for this with this slide. And coming to the next slide, challenges we faced in the DRAM cache. Okay. Mainly, there are two types of challenge as mentioned in the slide. Challenge one says high data transfer overhead between the application buffer and DRAM cache. Okay, this slide explores unique difficulties arise when a DRAM cache. For basically, let's discuss the first challenge: high data transfer overhead between the application buffer and DRAM cache. The first challenge highlighted is a high data transfer overhead, that occur between the application buffer and the DRAM cache. In tradition, DRAM cache setups, data must be frequently moved between the two components to ensure that most common access to data resides in the faster DRAM cache. The movement is necessary to capitalize on DRAM's high-speed access capabilities, but it comes at a cost. The continuous shuffling of the data creates a substantial overhead, which can negate the performance benefits of using DRAM as a cache. This overhead manifests as increased latency and reduced throughput, impact overall efficiency of the file system. We all know that what throughput is. And this is basically the challenge one. And coming to the next challenge, significant cache tags from the data synchronization and migration. I'm sorry. Okay. Now, the second challenge that arises from the need for the data synchronization and migration between the DRAM and the PM, persistent memory. The cache tax refers to the performance penalty paid due to overhead involving in maintaining data consistency and coherence across different data types. When data is modified in the DRAM cache, those changes must eventually be reflected in precision memory to ensure durability and reliability. That this synchronization process involves complex operations such as write backs, cache invalidations, which consumes the processing resources and time. Additionally, the migration data between the DRAM cache and precision memory to maintain the optimal cache utilization adds another layer of complexity and overhead. Coming to uh, flag catch, flag overview. Okay. This slide provides an overview of flag, the flat catch, FLAT catch, a novel approach designed to address the challenges associated with a DRAM cache in heterogeneous memory architectures. Flag integrates DRAM cache with virtual memory management, aiming to optimize performance of the file systems that utilizes the DRAM, both volatile DRAM and non-volatile precision memory. The integration, the integration of the DRAM cache with virtual memory management in the flag is pivotal in reducing the overhead and inefficiency typically observed in traditional caching methods. By treating the DRAM cache as a part of the virtual memory system, flag can be more efficiently managing data placement and movement, ensuring that the frequently accessed data persistence, sorry, access data resides uh, data resides in the faster DRAM while maintaining the persistence of the persistent memory. The two key techniques of this flags design is, as mentioned in the slide, zero copying caching, parallel optimizing cache management. We will discuss more about these two topics in the upcoming slides. Coming to the next slides, yeah, the zero copying caching. Uh, as I discussed above, this is one of the key technique in flags design. Okay, this slide mainly explains the importance of the concept of zero copying caching, a crucial technique used in a flag cache to enhance the performance of the file system on heterogeneous memory architectures. Zero copying caching addresses the high data transfer overhead by eliminating unnecessary data movements, thus significantly improve efficiency and speed. And this comes under heterogeneous page table and the page attaching mechanisms. Let's start with the heterogeneous page table. Unifies the heterogeneous memory into single level. The first key component of the zero copying is this heterogeneous page table. In traditional systems, DRAM and persistent memory are managed separately. Requires data to move and copy between the different memory levels. The heterogeneous page table in the flag unifies these disparate memory types into a single address space. This unified approach simplifies memory management and allows for the direct access to data regardless of whether it resides in the DRAM or persistent memory. By treating the combined memory resources as a single level, the system can more efficiently utilize available memory, reducing the complexity and overhead associated with the data movement between the different memory types. Page attaching mechanisms is the other zero copying technique. Part of zero copying technique. Optimize, yeah. Page attaching mechanism optimizes, as mentioned here, written in the slide, optimizes data transfer between the application and the cache. The critical element in page attaching mechanism is which further optimizes data transfer between the application and the cache. In addition, in traditional caching system, data often needs to be copied from the application buffer to cache vice versa, introducing latency and consuming additional resources. The page attaching mechanism in flag attracts application page only directly to cache without requiring intermittent uh, copying. This direct attachment allows for the zero copy data transfers, where data remaining in the place while being accessed by both the application and the cache. This mechanism, this mechanism drastically reduces the overhead of data synchronization and migration and resulting in faster data access and lower latency. Together, Together, these techniques form foundation of zero copying cache in flag. This leads to the more efficient memory utilization and reduce latency and improve systems. Then this giving more about the page attaching mechanism. This slide explains more deep about the page attaching mechanism. The optimizing data transfer between these optimizes data transfer between the application cage in traditional file system. Data transfer between application buffer and the cage can introduce significant latency and overhead, as mentioned in the above. The, and the heterogeneous page table, the heterogeneous page table unifies different types of memory into single address space. This integration simplifies memory management, allowing applications to seamlessly access data regardless of its location and DRAM or precision memory. Direct attachments of pages. Instead of the copying the data between the application buffer and cage, the page attaching mechanism directly attaches the application pages in the cage. This zero copy approach minimizes data movement and significantly reduces the latency and overhead. These are all the uh, part of flat FLAC or flat cage. Okay. Yeah. A few benefits here, as I already said, page attaching machine here, reduce the data transfer overhead because and direct page attachment eliminates a redundant data transfer, enhance the performance by reducing the time spent on the data movement. We won't give time. Generally, we used to takes time to movement from this cage to application cage, but here we are not movement, we just reducing the time, improve data access speed, and the speed also increases with the no movement. With direct access to cache data, application experience lower latency, leading to faster read and write operations, efficient memory access utilization. The unified address space and zero copying cache ensures efficient utilization of both DRAM and PM, maximizing strengths of each memory type. Okay. The other improvements are page remapping optimization. This slide mainly discusses this is also page remapping optimization also part in flag cache. I mean flag cache, which are crucial for enhancing the data transfer efficiency and maintaining high performance in the file systems. Utilizing heterogeneous memory architectures, these optimizations focus on improving data management through efficiently page handling techniques. These pages remap optimizations, sliding window buffer, batch faulting and detaching, and the new cache management mechanisms ensures data consistent high concurrency. Are integral to the flag's ability to enhance data transfer efficiency and maintain high performance. They collectively address the challenges of data management in heterogeneous memory architecture, ensuring the flag can deliver consistent and responsive performance even under demanding workloads. The next slide will give a practical implementation of benefits of this optimizing in real world scenario. Coming slides, I mean. Yeah. The parallel optimized cache management. The parallel optimized cache management technique is employed by FLAC, same as flat cache, to enhance the performance of file system in heterogeneous memory architectures. These techniques are designed to efficiently handle concurrent data operations, ensuring the cache remains responsive and efficient even under the heavy workloads. These parallel optimizing cache management techniques two-phase flushings and asynchronous cache mishandling are integral to Flex ability to maintain high performance and responsiveness in heterogeneous memory handling environments. By minimizing the overhead of the dirty data synchronization cache misses, Flag ensures cache can handle the concurrent data operations efficiently, providing a robust solution for optimizing the file system on advanced memory architectures. And coming to the next slide, flag file systems. Okay, flag file systems is high performance file system built on innovative flag framework, often significant improves in file read and write operations. Its success underscores the effectiveness of the flags technique and the highlights of the potential for the further advancement in the file system design for the modern computing environments. The subsequent slides will divide into environmental setup, key finding validating these performance claims, and flag file system represents significant step forward in system design, demonstrating the practical benefits of the integral advanced memory management technique to optimize performance on heterogeneous memory architectures. Moving to the next slide, experimental setup. The experimental setup for evaluating flag file system combines detailed micro benchmark with real-world application tests. This comprehensive approach ensures that performance improvements and benefits of flag file systems are thoroughly accessed and demonstrated, providing a solid foundation for the claims of enhanced efficiency and effectiveness. The subsequent slides will present the key findings and quantitative results from these evaluations, highlighting the significant performance gains achieved by flag file systems. These slides also explain how delegated user level virtualization can improve security in virtual environments by using user space hypervisor like divisor and deviation extensions. Coming to key findings, these key findings highlights the limitations of the conventional file systems and cache approaches in the heterogeneous memory environments, and they demonstrate the value of DRAM caching, impact the data transfer overhead, and burden of cache tags. And these presence of this finding underscores the effectiveness and benefits of flag framework in optimizing file system for the heterogeneous memory architectures. Coming to the quantitative analysis, the quantitative analysis underscores the performance benefits and strategic advantages of using DRAM cache in heterogeneous memory systems. It highlights the substantial performance gap between precision memory and DRAM, importance of optimizing data locality, compatibility of POSIX semantics, and with advancing achieving significant performance improvements in the real world applications. Coming to the next slide, benefits of FLAC. Yeah, it unifies address space and simplifies data management. Zero copying caching reduces data transfer overhead, already discussed. Parallel optimizing management enhances performance. This is all discussed in various forms here above slides. Okay. Evaluating results. The evaluation result flag file system showcase a significant performance improvement achieved through integration of flag cache techniques. The results are based on micro benchmark and real world application tests. The test result is based on micro benchmark and real world application tests and demonstrate the practical benefits of the flag file systems over traditional DAX-based cache file systems. And real-world application up to 10.6x to 9.9 speed up over the direct access based on cache file systems. Conclusions. In concluding, the presentation highlights of the significant achieved by flat cache and its applications in flag file systems, showcasing showcasing its transformative impact on file system performance within the heterogeneous memory architectures. By leveraging the key innovations such as unified address space and zero copy caching and parallel optimizing system and managing techniques. Flag addresses the critical challenges of integrating DRAM and precision memory. The unified address space simplifies the data management by treating the DRAM and precision memory as a single entity, reducing the complexity and overhead associated with the data transfer. Zero copy caching enhances the efficiency by minimizing data movement and latency, while parallel optimizing movement technique like two-phase flushing, asynchronous cache mishandling ensures that file system can handle high concurrency workload within minimal performance degradation. And this is conclusion. Thank you. Thank you, sir. Thank you for giving me wonderful opportunity to present this project. I hope you like this project. Thank you. Presentation.